Well, welcome back. Now it's been, what, 10 days since I've seen you last? Something like that. So, welcome back. We're going to go ahead and get started. Just by way of information, once again, there's a PLC this week, and it's going to be PLC 9 because last I checked, this is week 9. Or if we were lucky, it'd be week 10, and week 9 would have been spring break, but it's not to be. So the usual situation with this, it's for Friday. We'll see how we go about getting what we need to done for it. It involves a PV diagram, which should be fairly familiar, at least at this point. And then a couple of other questions about some stuff that we haven't talked about, but hopefully we'll be talking about today, and it's known as ideal gas kinetics. Or if you like, it's on ideal gas kinetic theory, and that's what we're going to be talking about for the next couple of days. We've got homework 4, is that right? This homework 4 is going to be due on Thursday this week, which for me is tomorrow. And so, as usual with that, we will have quiz number whatever it is, which I can't remember at this point. So that will be up and running all day tomorrow, okay? Other than that, I don't think I have too much else to say to get things going, but lab on Friday, we will have lab on Friday, and we'll go from there. So, we had just, if I remember correctly, we had just started this so many days ago. Anyways, in the meantime, I hope you enjoyed a little bit of time to relax. And if not, then I hope you got to do stuff that you like to do in your spring break time. And your extra day, which was Tuesday, so for me yesterday. But yeah, so I don't know. I've never seen a Tuesday holiday just coming on in the middle of the semester like that. I think that's the first time I've seen something like that. But anyways, that's good. Every day something new. We're going to continue with the analysis of the ideal gas from a mechanical standpoint. So if you remember, and this basically goes under the heading of kinetic theory of the ideal gas. If you remember, we had looked at the wall of a container. The container has a gas in it to the right here, and I have not drawn the other boundaries of the wall, but we'll assume this is a rigid and, for all intents and purposes, infinitely massive stationary wall when compared to a molecule. And the molecule comes in and hits and bounces off like so, such that we looked at its momentum, right? Its momentum incoming, its momentum outgoing. We're assuming an elastic collision here, perfectly elastic, such that it preserves its kinetic energy. So if it is an elastic collision, then we have a momentum change. And in this case, our delta P, which I'm going to say in the x direction, so delta Px, I'm going to say my x direction is going to be positive that way. So the initial momentum would be negative mvx, right, in a classical sense, mass times velocity in the x direction. The final momentum would be positive mvx, so we ended up here with final minus initial, and therefore the change in momentum is twice what the value of the momentum is. We took this and wanted to then look at what force did the wall exert on the molecule, and vice versa, what force did the molecule exert on the wall. So the average force exerted would be during a time interval, and we could use Newton's second law as written in the original form that the average force, I'll just call it force average here, is delta P x. And I should label this as average force in the x direction, F average x, divided by some time interval, which could be, for example, we'll look at that in a minute, but for example, that could be the time between collisions, right? Or the time during which this collision lasts. So in this case, I know what the delta px is, right? That's just the twice the momentum. And the time, if we think about, okay, what happens when I consider more than just one molecule, the time is going to start to get put onto, well, how many collisions per time would there be? So imagine that instead of just the one molecule, so here we'll just say for one molecule of gas, or I told you this before, and it's just semantics, but technically we're not supposed to talk about molecules. It's a gas particle, whatever it is that makes up the gas. Thermodynamics doesn't know anything about stuff like that. We have to have the atomic hypothesis for that. But nonetheless, we're going to, because we know at least that they're useful to talk about. So for one molecule, the average force in the x direction would be average F. Let me do it this way. Let me do Fx average would be 2 mvx per time. Okay. Now we have to start thinking about, right? I brought in this really amazing demonstration today. So I just wanted to use this as the wall. Okay, so here's the wall, and I've got a molecule. I've got basically a gas particle hitting it. Okay, so here's the wall like this. I'm going to think about this as just one section of the container. Say maybe the container is bigger and comes out like this or whatever. But inside here, right, are a number of these gas particles. Okay, so the gas particles are going to be, at least in this case, we can consider them to be moving initially only left or right. We'll expand to more dimensions in a little while. But think about all the molecules that are within this thickness right here, okay? And I want to know how many collisions are going to be happening within a certain amount of time. Well, what I can do is think about all the molecules that are within here that would have the chance of hitting the wall and try and estimate about how many of those are there, okay? So we're going to take, so for capital N molecules, we're going to take and think about, all right, the force now is going to be the force for one molecule multiplied by the number of collisions that happen in the time delta t. Okay, so now the average force in the x direction is going to, I did it backwards. It should be x average, fx average equals, there we go, the same thing, what it was for one molecule, multiplied by the number of collisions. And I called this, I think last time I called this number of COLL collisions. So if I want to find out the number of collisions that happen in a time interval, then I can do that by considering, right? What I was saying was, if I just said, right, look at all of the molecules that are within this volume. Now remember, that's a volume, right? Because it's a box. And so I have a volume's worth of air. I don't know if you can quite see this super well, but yeah, kind of, right? It's a box. And so I'm considering all the air within here, and I want to know how many of the molecules that are in there are going to be hitting that way in a certain time interval. All right, so that number of collisions is going to equal basically, how many particles do I have in here? And then I'm going to use a statistical average, okay? Because there are too many particles to enumerate precisely. So I'm going to go to the macroscopic view of this, and I'm going to say, okay, on the average, how many of the particles that are contained in here, and I'll draw a few more in, how many particles that are in here are going to be traveling to the left and are therefore going to hit the wall, okay? Because we're pretty sure that outside this area, if I think about that one, it doesn't have the right, it won't have the right, gosh, what am I trying to say? It won't hit in the time interval. It won't be hitting in the time interval, right? So I'm thinking of this, I'm thinking of this x velocity kind of as an average, right? I'm already kind of putting in a statistical average whereby, yes, I know that they don't all have the same velocity, but suppose, or the same speed in the x direction, but suppose that they do, right? And so on the average, how many of these things in this volume will hit the wall? Well, they won't all, because some of them are going to be going, let's do this one. Some of them are going to be traveling this way. This one right here is not going to do it. It's going to be, it's missing. It's going that way. All right, but this one will hit, and that one will hit, but this one's not going to, and that one's going to hit, but this one's going to hit that one and bounce off, and then this one's going to hit that one and bounce off. Right? So there are so many molecules in here that are exhibiting random motion that we would be fairly well justified to liken this to the same situation as if I had filled this with a layer of pennies, right? And then I had gone, or banged it, right? And said, how many come up heads and how many come up tails? And I've done this a couple of times, and I found that more often I get about a 50-50 divide, right? Now, I don't always get a 50-50 divide, but statistically, the average is half, right? Because if I just take the pennies and I go like that, and I count them up, why would they have one versus another? Right? Assuming we've got honest pennies here. So the same thing's going on here. I'm assuming I've got honest molecules here, but you can never trust an atom. Yeah, I don't think you can quite read this, but that's okay. Never trust an atom, they make up everything. So if they are being true to not caring what they're doing, then half of them will be going to the left and half of them will be going to the right. So I should be able to write an expression for the number of collisions that are going to happen in a time interval. All right, so let's go a number of collisions in time interval, delta t, okay, should be equal to the number of particles that I have in here. But that would be like saying I want to take the density and multiply by the volume. Okay, so I'm going to use the number of particles within this distance here, which happens to be Vx times delta t. I'm going to take the number of particles within Vx delta t by saying density times volume to give me the number, and then I'm going to take that number and I'm going to multiply by half, because that's the statistical average of half of them going to the left, half going to the right. All right, so statistical average. If I do this, the density is capital N over V. Right, that's the number density of the gas, no matter how big the container is or whatever it is, I've got a density of gas in there. Just like if I was in this room and I just said, okay, what's the density of gas within here? Well, it's the density of gas everywhere. We're assuming this is in thermal equilibrium. The volume is whatever the cross-sectional area of this wall is, right? So I'm looking at the wall and I go, oh, there it is right there. It's the cross-sectional area of the wall. Boom. Okay, that area. And then Vx delta t is the thickness of this thing here, is this thickness right here. So I'm going to multiply by the thickness, and then I'm going to multiply by the half, and that should give me the number of collisions that are going to occur within this time interval. All right. Now I think this is about where we had gotten to last time. So let me go through here and say that I'm going to pick up with my number of collisions into this expression here and work on getting what the force looks like for n molecules. All right, so this is force X average, okay, is going to be 2 mvx divided by delta t, multiplying all of that, capital N over V, an area of Vx delta t, and a 1/2. All right, so this is not I don't know. I guess I should maybe have prefaced this with, I'm going to go through and do a lot of this, but really what the point of all this is not the math. It's not the intermediate expressions. You'll see what the overall expression looks like in the end. But really what I want you to think about is the reasoning going from one step to another and understanding how I did this reasoning right here by just thinking about how many particles are in there and writing down this expression. Okay, so it seems like I just wrote this down because I made it up, and that's kind of true. I did kind of just make it up because what I'm thinking about is the number of particles in this volume. How do I calculate that? So I'm going to write down this expression for it based on density and volume, and I'm going to take a statistical average. So the math is just kind of popping out of nowhere, but I want you to understand why I'm doing the steps that I'm doing, all right, rather than, and you can go back later if you like and make sure you're solid on what all the math steps are. So what we're going to do here is we're going to say, I can do a bit of simplifying. What I want to ultimately do is one more thing, which is that you'll notice that this is the X average force. Okay, but what if I consider the ceiling or the floor or the other sides of this container? Would I be able to write down similar expressions for those situations? I think you could justify the answer to be yes in these cases. Now, what that means is that I don't want a force in the X and a force in the Y and a force in the Z. I just want to be able to talk about what force is exerted, because ultimately my goal is to try and get an expression for the pressure exerted by the gas, okay? How do I do that? Well, I'm going to take this A pretty soon and I'm going to slide it over here. And that force divided by the area is going to give me a pressure, but I don't want to do that right now because that is not complete. I want the full force in all three dimensions so I can talk about a pressure, right? I don't talk about a pressure that way and a pressure that way or a pressure this way. You talk about the pressure, right? So it should be exerted in all directions by a gas. And why? Because that's what we observe, right? That is what is experimentally found. So my goal is the pressure, but I need to deal with these Vx's. So I need to expand to 3 dimensions now. And what that means is I need to think about, the velocity, Vx, Vy, and Vz, as being components of a total velocity, right? These things don't just have velocity in one direction. They are all over the place, okay? So now I'm going to use a little more statistical reasoning in trying to assess what's happening. So I'm going to talk about the total velocity of a gas particle, of a gas molecule. Total velocity, V, right, is a vector quantity and would be written like this with these components. I'm not sure if you're aware of the triangle brackets for vector components, but essentially that's what these are, right? It's V. Do you still use I, J, and K hat, or is it X, Y, and Z hat? Whatever it is. It would be like this in the I hat direction or in the X hat direction. Why do they use I hat? X hat is so much easier because you know where you're going. Anyways, X hat, Y hat, Z hat, or I hat, J hat, K hat, right? And that's the vector expression for this thing. So when it comes to thinking about an average, right? I want to think about a statistical average. When I look at this expression, I'm going to notice I've got a factor of 2 velocities here. Okay, so I'm going to get a Vx squared. That means what I should probably be thinking about is not one of these particularly, but the square of it. So I'm going to take the velocity and I'm going to, if you like, just in case you're worried about notation, so that's the magnitude squared of the vector, right? And that should be basically the dot product of the vector with itself. And so this would be Vx squared plus Vy squared plus Vz squared. Okay, and now what are the chances that the velocity in the x direction, the velocity in the y direction, the velocity in the z direction are noticeably different? Okay, if I'm thinking about a situation in which the gas has come to thermal equilibrium, in other words, I don't have a pocket of hot gas right here. Hot pocket. I don't have a hot pocket of gas right here. And therefore this one's going, oh my gosh, I need to warm up and because this thing's going to transfer heat to me. And I got, no. Everything's already all smoothed out, right? The gas is at a uniform temperature and there's no significant outlying differences. It's in equilibrium, okay? So the probability of the contribution of each of these velocities in the different directions, I mean, this is just down to convention, right? Which way is x? What if I made x that way? What is going this way? Or what if x was this way? Or what if x was that way? Who knows, right? I should be able to divide it into 3 coordinates. But when I think about the contributions of each one of these, why would they not be equal? So in other words, I should be able to write, and let me put this little slice of reasoning in here, since we would expect the gas to be distributed uniformly and have a uniform temperature, then we would be able to say on the average that each of these contributes exactly the same amount to the total velocity, because all I'm doing is picking a set of coordinate axes at random. Well, who's to say I'm picking this one versus that one versus this one versus that one, right? So, so since the gas should have no preference for one of these directions over another, all of these should contribute equally. I would say that the gas does not prefer one direction. I don't know. Did anybody prefer one direction? Maybe they did. Over another. Okay. So in other words, the average. So I'm going to call it Vx squared average should equal Vy squared average should equal Vz squared average. And therefore, they all contribute the same amount to the total velocity, and that means I can write any one of them as say Vx squared. I'm going to pick Vx squared because that's the one I'm dealing with up here. Vx squared average would equal 1/3 of the total V squared, like this. All right. That's a piece of reasoning that I spent a little bit of time talking about because it may not seem directly intuitive right away and it may seem like a bunch of hogwash, but it really gets back to the idea of what thermal equilibrium means. What thermal equilibrium means is that the energy is distributed evenly. There is no preference for one direction or one velocity over another. Why would the gas suddenly want to move that way more quickly than it moved this way or this way? Right? It doesn't, I was going to say it doesn't think that way, but it doesn't really think at all. So that's not really a fair argument, and that's anthropomorphizing, so I don't want to do that. But the point is here that if it's evenly distributed, then this should be a reasonable conclusion to arrive at. That means, I'm going to have to get rid of my picture now. That means that when I look back at all of the total expression that I have here, I want to expand it into 3 dimensions. And so my expression is going to now look like, instead of fx average, it should just be f average. F average. And now I can go do a bunch of cancellations of stuff. I'm going to notice that I have a Vx here and a Vx here. And as we've already noted, that means it's Vx squared. And that means I can replace that Vx squared with 1/3 of the total velocity squared, which is much more useful. I have a 2, which cancels with a 2. I have a delta t, which cancels with a delta t. I'm going to put the n over v here. I'm going to put area. I'm going to put mass. Mass is left over. N over v area, Vx, and the 2 is gone. So now I've got Vx squared, but my Vx squared should just be, oops, sorry, 1/3 of V average squared. Well, let me write this a little bit more properly. V average squared. No, wait, hold on a sec. V average squared. There's a thing that I've got going on here. I don't want V average squared. I want V squared average. Sorry. Let me write this a little bit more appropriately. V squared, oops, V, come on, let's try that again. V squared average, there we go, V squared average. Okay, that's what I want. And therefore, oh, I forgot the mass. Didn't I? Yes, I did. I forgot the mass. Dang it. Okay, I'm going to put it right up here on top of the 3. There we go, mass. Okay, now do I have everything? Because I just went and checked a whole bunch of boxes and I forgot what I had. I think that's it, okay? Okay, real quick. I was looking for pressure, and so what I want to do ultimately, like I said before, is swing the area underneath here, and this should give me a pressure. Because the pressure is the force divided by the area upon which the force is exerted, right? And that just is straight back to this thing right here, and we're thinking about the area of this thing as just boing, 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 right? It's getting hit a lot. So force per area means I swing that underneath, and that means I get a 1/3, I get an N over V, and then I get this quantity M, V squared average. Okay, now let's talk about how to take the average. This is going to be done by what's known as the root mean square process. So how do you take an average of something which has apparently, as what I've been saying here, which has apparently as many positives as it does negatives? Right? Isn't that what I'm basically saying? Like, well, I erased my drawing, but remember I said half of the molecules are going this way and half of the molecules are going this way. So what's the average? Shouldn't it be 0? Well, yeah, it would be, right? Because from a vector sense, going that way is equally as likely as going that way for these particles, right? So in order to try and get something that is more useful than 0, which as it turns out is not useful as an average in this case, we do what's called the root mean square, in which we kind of arbitrarily, and by the way, this is a very useful process. It's more used than just in esoteric situations like this. The root mean square is a way of basically taking the absolute value of something. In other words, I'm going to take all my values of the velocity, I'm going to square them. Boom, now they're all positive. I'm now going to take the average of those, and then I'm going to take the square root in order to undo the square. So this is known as the RMS value. Okay, that's the RMS value. Notice I do not actually have the RMS value here. This is like the RMS value squared, right? This is the square of the RMS value. It's the square. It's squared taking the mean, but I haven't done the square root of it. Okay, because I don't want just the velocity. Apparently, I want the square. So this is what I've got. Okay, so that's a little bit on how you calculate an average when there's pluses and minuses. And that, by the way, is a standard practice. That's something that people use. All right, we have this situation with the pressure in which it depends on the number density, and that kind of makes sense, right? Because the more stuff I cram in here, the more collisions I'm going to have, even if they're all moving at relatively the same temperature. Velocity, right? If they're moving at the same speeds, if I have a lot more of them, I'm going to have a lot more collisions just by number, okay? Of course, if I kept the number constant but increased the speeds, how would I do that? By increasing the temperature, by dumping heat in or doing something like that. If I had them moving faster, it would increase the pressure, right? So they're tattooing a little harder. Bam, right? Okay, so this is our pressure. What is often useful at this case is to realize, at this stage, is to realize we do have quantities that are similar to this. This looks like a kinetic energy. Right? Is this a kinetic energy? Yeah, it kind of is, right? mv squared. So if I just threw in a factor of a half here, then I'd have the kinetic energy. I'd have the average kinetic energy. But if I put in a half, I need to put a 2 in somewhere else, so I'll just put in a 2 here. But what that means is then I can write the pressure P, and I use the foot on P here, so it's not momentum, as 2/3 capital N over V times the average kinetic energy, which I'll just call the KE average. Like that. If I know the average kinetic energy, then it's just 2/3 of that times the number density. Okay, so this is interesting. All right, this is kind of maybe a nugget of truth that we're getting to. In other words, this seems to be a useful situation. Okay, and by the way, it took people a long time to get to this type of thing. An analysis of the gas particles is not an easy thing, but I think this is really cool stuff. Now what can be interesting is to take a look at this and maybe write it in a slightly more suggestive manner by multiplying the V over. If I did that, I would have PV on this side. And we already have an equation of state that has a PV on that side. Aha, what can we do? Well, we're going to notice that it's 2/3 times capital N times the average kinetic energy. And what that means is that if I think about the ideal gas equation of state, PV equals stuff, and PV equals this stuff, means that the stuff should be equal to this stuff. Okay, I'm going to compare this to, now I'm going to write this ideal gas equation of state as capital N here, in the capital N form. You may know this form already, although you may not. Typically in chemistry, you use the little n, the number of moles, times capital RT. This is the Boltzmann constant. K sub B is the Boltzmann constant. Capital N is still the number of particles. But this is exactly equivalent to little n times RT. It just so happens that we have a capital N here, so it's more efficacious to look at the capital N variety over there. Now, this is kind of cool because what it tells us is I have an N here and I have an N here, so whatever's left over must be whatever's left over. So I have a 2/3 here and an average kinetic energy and that must be the same thing as KB times the temperature. Okay, wow, that's pretty nifty. So what it's telling us is that the temperature is actually a measure of the kinetic energy, the average random kinetic energy that these things have. Okay, we say we can conclude, oh, that's pretty good right there. We conclude that 2/3 KE average equals Boltzmann constant times T. And the Boltzmann constant is, it's lookable, uppable, and it's a number. But what it does is it relates the amount of energy something has to its temperature. Very, very useful constant in terms of how constants go. But notice what this gets us. That means we can write T, the temperature of something, as being a consequence of the average kinetic energies of the molecules. I'm just going to flip this over, and no, I'm not. I'm going to write T as 2/3 KE average divided by the Boltzmann constant. And on the flip side of things, we can also write kinetic energy average as being related to the temperature. So if I wanted to do that, then I would leave the KB over here and write it as 3 halves, try that again. 3 halves KB times T. All right. Or. You write one or the other. But they're equivalent things, right? They're equivalent. So what it's telling us, it matters less how you write it, but it matters what it's telling you. What it's telling us is that either way you look at it, the temperature is a consequence of the main thing on this side that is under our control is the average kinetic energy. Likewise, if we want to control the average kinetic energy of the gas, all we got to do is change the temperature. Yeah? All right, so we're here, which is pretty cool. Now, what this gets us is a couple of other things. And I maybe can mention these. I can maybe mention these quickly now, and we can come back to them at a later point, maybe tomorrow. But there are a couple of interesting quantities that are involved. So one of them is the number of collisions. One of them is the time between collisions, right? That capital N collisions per time that I wrote out. Another one is, if I think about instead of per time, what about per length? How far does one of these things travel before it hits another molecule or another gas particle? Okay, that is also calculable. And it's known as the mean free path. The mean free path is the average length that the thing can go on its own before hitting something. That's what free means. This is known as the mean free path. I'll probably come back to that tomorrow because it's a little bit more of an offshoot type of thing and not directly super important at this point. What I want to get to is some more relationships that we can find out when we look at the ideal gas with this lens, right? With the kinetic energy being something like this and the pressure being something like this. All right, so let's take a look. I want to go to the first law at this point. I want to take a look at the first law and say, all right, so what happens when I look at the internal energy of the ideal gas, right? The internal energy of the ideal gas is this thing. Because, right, we're not working with potential energies. So let's revisit the first law. Okay. The first law tells us that the change in internal energy is equal to Q plus W, with all of the appropriate signage involved with the heat going in positive, work going in positive. This here, this average kinetic energy, is basically the internal energy of the ideal gas, right? So if there's a change in the internal energy of the gas, then we've changed this. And that's why I've been kind of hitting this point over and over, that if you change the internal energy of the ideal gas, it's because you changed the temperature, okay? So one of the consequences of seeing that is that when we look at this, a delta E internal, we now know how to write down a delta E internal. We have an expression for it now. This is huge. This is really a delta KE average, which means that it's 3/2 times K, the Boltzmann constant, and neither one of these is going to be a delta, right? We're not going to change these. What we're going to change is the temperature. So if you think about where the delta operates, when I look at something like this, if I want to change this side, it's because that changed and not these things. That means that when you look at the PV diagram, those isotherms really are zero temperature changes. Okay, they really are situations where you are not changing the overall speeds or kinetic energies of the molecules. You are changing how the heat and work are flowing in and out of the system. You're not changing the overall temperature of the system. Okay, so that's pretty cool. We now have kind of an understanding of what the internal energy looks like that we didn't have before, although we were kind of dancing around it a little bit. Let's take another look at the heat and the work from this perspective. Now, we had the heat already. We know that for an ideal gas, it does not change state. Therefore, all heats are sensible heats. There is no latent heat in the ideal gas, because if it latent heated, it wouldn't be a gas. So, when we talked about how heat affects the substance, we talked about this thing, MC times delta T. That's the specific heat per mass, right? Well, I guess specific means that. It's the heat capacity per mass. That's what specific heat means. It's a specific heat capacity. I can write this in a slightly different way. When I think about what was I just going to say? When I think about the number of moles that I was talking about before, I can write this. This is kind of a mass-based thing here, right? I could also write it equivalently as the number of moles times this other quantity, where this other quantity is, I'm going to call C with a sub V on it here. This is the specific, this is the molar specific heat. This is still a sensible heat transfer, but instead of using masses, we're using moles, okay? Masses, moles, and therefore this quantity is slightly different than this one, but they play the same role, okay? And of course the delta T is the delta T. Let's take also a look. Well, wait, before we do that, let's talk about what moles are. And maybe you've run into them in chemistry, maybe you haven't. And we have not really had to calculate them in this class because we have generally assumed that they're constant, right? Our systems are a fixed number of moles or fixed amount of stuff. Maybe let's just go through and talk about what that means. What is a mole? Well, it's a really kind of trying not to impugn people too much anymore. I'm trying to turn over a new leaf, but it's kind of a dumb name. I don't know why moles, but moles because it's kind of related to molecules. Okay, fine. But anyway, it's an amount of stuff. Okay, it's not the small furry rodent. It's an amount of stuff, just like you have a dozen eggs. So if I said, hey, I'm going to go buy 50 eggs, and you'd say, well, how many dozen is that? You would already know how many dozen that is, right? That's would be 4 plus 2 extra, right? So you'd have 4 point about 2, 4.16, say, dozen. Well, moles are basically the same exact thing. The moles are how many particles are there in the gas or in the system or whatever you like, compared to, units of this number. So instead of a dozen, like saying my unit is 12 eggs, the unit for this is Avogadro's number. Avogadro's number is a pretty cool number. Very simple to remember. It's just like you're dialing them up. If you can remember your phone number, right? 602-1023. Hello? Can I talk to Avogadro? It's just a number by which it's convenient to say that there's an amount of stuff in those units. How many Avogadro's number worth of stuff do I have? 2, 3, 4.5? Who knows? But that ultimately is the number of moles. Avogadro's number is 6.02 times 10 to the 23, and it's a big number, but when you get that number of things, you have 1 mole worth of stuff. You have 1 mole worth of stuff. Okay, so capital N being capital N, where's my capital N? Capital N, I erased capital N. All right, so if capital N is 6.02 times 10 to the 23, then little n is 1. And that means I can write the number of moles as being how much stuff do I have divided by Avogadro's number. Exactly like we just did 50 eggs divided by 12 dozen, right? There's 12 eggs per dozen. So it's the same idea. Hopefully that helps. Whenever you look at the periodic table, you will notice the atomic weights are given in grams per mole. And this means and mole is usually abbreviated without the E on the end, so it's just MOL. The atomic weights are some number of grams per mole. That means they've standardized it, right? It's like you take the weight of a dozen eggs. Right? How much do they weigh? Well, they weigh this much. Okay, well, I'm going to take 1 mole worth of this, and I'm going to weigh it's this many grams. Right, so air weighs, I don't remember what air weighs, but it's something like 15, 18, no, air, oh no, wait, water vapor is 18, isn't it? Where's my periodic table? Anyways, hydrogen is 1-ish gram per mole, helium is about 4, etc., etc. So anyways, they weigh these things, and that gives us the way that we know the individual chemical element weights or masses, really. I don't know why they're called weights, but they're the same thing. All right, so we're there. Great, so why don't we take a quick look at the work? Oh, wait, I need to go back and add one thing to this molar specific heat. The molar specific heat, it has this V underneath it. Forgot to mention this. The V underneath it, okay, means it's taken at constant volume. That's what the little V under here means. So please make sure you add that back in because I forgot to say that. The molar specific heat at constant volume, because we're about to look at one in which there's another molar specific heat that we're interested in, okay? Since we look at PV diagrams, okay, the molar specific heat at constant volume would be equivalent to how much heat did I have to add to go from 1 to 2 at constant volume, right? So this is a completely heat-only process. You know the temperature went up because it's at a higher isotherm, and you know that there was no work done because there's no area under the curve. Therefore, the only way you ascend from 1 to 2 is through heat transfer, and that means that I've done something like this in order to change my internal energy. Okay, when that happens, what you can notice is that during this process, so 1 to 2 during a constant volume process, what will happen is that the internal energy change is completely due to that heat. So that means that Q equals delta E internal, and that I can write as NCV delta T equal to 3 halves. Now, I have to make sure that I multiply in all of the, number. So for the entire, because I'm talking about number of moles here, I'm going to multiply by capital N the number of particles here and say that when I have a delta KE average, right, that the 3 halves KB delta T, that's for each particle. So I need to multiply by the number of particles. That's where the capital N is coming from. When I look at this, I'm going to find out a relationship about how much this molar specific heat is going to be in terms of physical constants. Okay, so watch what can happen. I can take away the delta T's, and I can try to figure out what is the molar specific heat of an ideal gas. So CV, right? This is for an ideal gas at constant volume. I'm going to say the CV. I got to swing the little n underneath here, and I'm going to have 3 halves capital N divided by little n times KB. When I said it was in terms of physical constants, you'd say, well, wait a sec, that's all dependent on how much stuff you have. Well, no, it isn't, because if you look up here, these are really related by the Avogadro number, right? So it's really like I just switched these two here, and that this thing right here is equal to the Avogadro number. Therefore, this is really just 3 halves times the Avogadro number times the Boltzmann constant, which tells you that the ideal gas specific heat, the molar specific heat, does not change with temperature. Therefore, when I go from here to here, the only thing that matters is how much heat am I putting in, because it raises the temperature the same amount for the same heat that I'm putting into the gas. This is great because that means I don't have to worry about, well, when the temperature goes up, do I have to add more heat in order to increase the temperature more? No, I don't. It's the same no matter what the temperature of the gas is. And furthermore, I'm just going to let you know this. This number here is something special. This number is the capital R number, which is known as the gas constant. And for my units, this is 8.31 joules per mole per Kelvin, like that. There are other numbers that you can put in for R because you can have stuff in atmospheres, and basically there are other chemical units that can be important to chemist people, but basically they're not important to anybody else. So the joule per mole Kelvin is mostly the one that regular people would use. And that would be what you would say to the person on the street. You can certainly, I think, remember that number easily anyway. 831. For those of you who do not live in this area code, then it's not that easy to remember. So there you go. And I see that people driving around with this on their bumper sticker. That's pretty cool too. 831. They got the gas constant on the car. Okay, so we've reached the idea that the molar specific heat is a constant number. It's just 3/2 times R, and it doesn't matter the temperature. Is that really true? It turns out that experimentally, yeah, for an ideal gas, like for a sample of air or pure nitrogen or things like that at different temperatures, as long as they're well above the boiling temperature, right, which air is, then the amount of heat is the same to increase the temperature by the same amount. All right, so we have that. We also have another interesting situation. Okay, we have another type of process on the PV diagram here, in which we have talked about the pressure being constant, like so. Perhaps this is A to B, and that's isobaric. So what happens during an isobaric process? Well, now we have work being done, right? And we know the work being done is the pressure times the delta V. Pressure times delta V. I can rewrite the first law for a situation in which we have an isobaric process and an ideal gas. Okay, this we know. We already figured this one out, but we'll just go with delta E internal for now. So this is going to be an N, a C, but this is no longer a CV, it's a CP, because the molar specific heat at constant volume would have been that one. I'm adding heat at constant pressure, which is this one. So this has a P underneath it. This is now the molar specific heat at constant pressure. All right, and I'm going to put the delta T in here. This is the equivalent to a MC delta T again for the heat transferred. And we know that work in a process going that way should be, that would be negative P delta V. So this would be negative P delta V, like so. And good news, I can rewrite P delta V. If I look back at the equation of state of the ideal gas, P delta V should equal NR times delta T. Right? If I delta the left side of the ideal gas equation of state and I delta the right side of it, the N is not changing, right? The T is changing though, because I'm crossing isotherms by doing this. All right, so I'm going to use NR times delta T here, and I'm going to find that this is equal to, let's go here, this is equal to N times CP delta T minus NR delta T. A very interesting situation here, because I've got an N and a delta T in each term. I'm going to go back to thinking about what the ideal gas's change in internal energy looks like. All right. This is going to look like N delta T times CP minus R. Okay, so if I just factor out the N delta T, I get a CP minus R here. Okay, but what is the internal energy change for the ideal gas? Well, interestingly, we kind of already figured that out. And it's a little weird to think of it this way, But we already know that the internal energy change is equal to 3/2. What did I have written over there? N KB delta T. All right, the internal energy change is already this. We already know, however, that 3/2 times the NKB, or no, 3/2 times the KB, NKB delta T, is the same as little n times capital R delta T, right? It's the same thing as this. And that's going to show you NR delta T. That the 3/2 R right here, the 3/2 R, that's the molar specific heat at constant volume. Okay, so this leads to a major stumbling block that I want to make you aware of. That thing right there, when you use the internal energy change, what you're finding is that you can write the internal energy change in terms of the molar specific heat at constant volume. That does not mean that you have to be going through a constant volume process. So maybe it's easier if I don't do it that way. I just want to let you know that it is done this way, that no matter what the process, the internal energy change is written this way. And that can be confusing because I just got done telling you that this is the molar specific heat at constant volume. But really all it is it's a name, right? That's just a variable name for 3/2 times R. So it might be more useful to think of the internal energy change as this thing instead of having it be the CV. Okay, the reason I want to include the CV is so that I can get the relationship between the ideal gas molar specific heat at constant pressure and the ideal gas's molar specific heat at constant volume. So I'm going to do it this way for a minute right now. This is only because I called CV equal to 3/2 R. Okay, that's because CV equals 3/2 R. It does not actually carry the you must be going through a constant volume process with it, which is, yeah, anyways. So point being here that this thing is equal to that thing. And that means I could write this as N CV delta T. And the relationship that we're finding about CV and CP is that CP is equal to CV plus R. Meaning that if I think about the molar specific heat at constant pressure, it will be bigger than the molar specific heat at constant volume. And the reason why I'd like you to think about why. Because what it's telling you is that if I add a certain amount of heat at constant volume, it raises the temperature by a certain amount. But if I take that same amount of heat, right, if I add 10 joules of heat to this thing, I'm going to raise the temperature by, I don't know, almost a degree, say. But if I take that same 10 joules of heat and I add it at constant pressure, I'm not going to increase the temperature by almost a degree. It's going to be like a half degree or maybe less, right? I want you to think about why that is. Why would the specific heat change based on the conditions of how I'm adding the heat? This is an interesting little brain twister as to why those are different. But nonetheless, what we're finding is that they are, because N delta T here and N delta T here means that whatever's in here must be the same as this. So the two molar specific heats are related, but only by a constant, right? Okay, so that's the start of thinking about the ideal gas as a set of basically independently acting tiny bouncy spheres. All right, and that's what we're doing right now. We're just thinking of them as tiny bouncy spheres. Okay, when we did that, we found out some stuff, and it turns out that yes, indeed, experimentally, we can say that the specific heat at constant volume is approximately that for an ideal gas. However, there is a problem, and I will tell you what the problem is, because we have to address it. The problem is that when CV is plotted versus the temperature, and I just got done telling you that there was no change in CV with the temperature, and that's true sometimes. For a particular set of gases, that's true. But it's not true for every ideal gas. It's really kind of strange. Some ideal gases, it's absolutely true. But other ideal gases, it's not. So, what we find is that down here at basically low temperature, right? We'll have this specific heat, the molar specific heat constant volume, be 3/2 R. And that's great. But after a while of heating this gas up, it does that. And it jumps up to 5/2 R. And very, very interestingly, oops, I'm going to have to rearrange my axes here. Some will even jump up to 7/2 R. So the question you have is, well, what is going on here? Okay. Now, I'll tell you the difference in the gases. There are differences in the gases that do this. Like I was telling you, some gases are flat and they stay right here the entire time, and they never do this. Those gases are found to be the noble gases, or the rare, I don't know, what do you call them? The helium, neon, argon, krypton, xenon, radon, those ones. I don't know what you call those, but I know what they are. So it turns out that those are a different shape than, for example, air. Air is not the same shape as the noble gases, because the noble gases are one thing only. They're known as monatomic. And so if you take a monatomic ideal gas, it will have that specific heat all the time. Won't change. But if you take a diatomic ideal gas, in other words, a nitrogen, which is N2, and can look like a little barbell, you will find that at higher temperatures, its specific heat will increase. Specific heat at constant volume will increase. And furthermore, if you take that same gas up even further, you'll find that it increases to 7/2. Right? So the question is why? Monatomic just looks like a ball. Diatomic looks like a barbell. Right? That's a diatomic molecule. And nitrogen does that, and oxygen does that, and I don't know, a bunch of other gases do that. Okay? So the question is, why is that happening and what's going on? So what's happening is a very interesting thing. What's happening is that when you talk about the monatomic case, and I add heat to a monatomic ideal gas, how can that energy get stored? The energy gets stored in one of three ways. Kinetic energy that way, kinetic energy that way, kinetic energy that way. That's all there is. A monatomic ideal gas has no other thing to do. It won't store any energy any other way. It moves that way, it moves that way, it moves that way. So there's kinetic energy involved in those three dimensions. At lowish temperature, a diatomic molecule would do the same thing. But notice, if I think about the diatomic molecule at slightly higher temperatures, I notice that the CV increases, and I've got, right, that 3 right there described the motion in 3 space, and therefore I've got 2 more ways to have energy here, right? That 5 means that not only can this barbell go this way, and this way, that's 3. Now, if I have it at high enough temperatures, it can start doing this, right? It can start turning like a helicopter blade, right? Like this, or like this. So those 2 modes of rotation mean that it can store more energy before it increases its temperature, because you're going to excite that mode or that mode, as well as this, and this. And I'll leave you to think about what happens when you increase the temperature even more, such that possibly that bond weakens a little bit. And all of a sudden now we're up at an even higher specific heat constant volume. Okay. Alrighty, so that's I think pretty much about what we need to say today, or is there a little bit more I could say? Well, do I have a few more minutes? Maybe I do, I don't remember. No, it doesn't look like it. Okay, I guess we're about done then. So we'll come back to this. The idea that I'm telling you about here, in which you're looking at the molar specific heats and the numbers involved, is a theorem known as the equipartition theorem. And basically, we've already used this. I just didn't tell you. The equipartition theorem is the one that caused us to be able to say, well, half of those molecules are traveling that way and half are traveling that way. Why? Because the energy is equally divided up. It's equally partitioned. So the equipartition theorem tells us that all of the ways to have energy are equal. If you fill buckets, it's the same thing, right? I fill buckets with water, right? If I have a bunch of energy and I'm dumping them all this, right? I'm filling each bucket up a little bit. I'm going to tell you that all the buckets are filled to the same level. That's what equipartition means. So we'll explore a little bit more of this on Thursday, that's tomorrow, and we'll also talk about the mean free path and a couple of more cool offshoots of the application of mechanics to the ideal gas. And at that point, we will be ready for a lab this week, and then we will pick up for a regular week next week. So don't forget, homework is due Thursday this week. That is for me, tomorrow. And quiz will be available on that day as usual. So I bid you happy rest of your day, friends. And I will be seeing you, for me, tomorrow. See you then.